Hey everyone, welcome back to the channel Code with AKJ. Today is day 54 of solving LeetCode 75 challenge, and today's problem is successful pairs of spells and potions. So before moving on to the problem statement, if you are new to the channel, make sure you like, share and subscribe to this channel for the latest updates. So right now we are in the binary search module and this is our second problem statement. So let's get started. So the problem statement says you are given two positive integer arrays, spells and potions of length n and m respectively, where spells of I represents the strength of ith spell and potions of j represents the strength of the jth potion. You're also given an integer success. A spell and potion pair is considered successful if the product of their strengths is at least success. Return an integer array pairs of length n, where pairs of I is the number of potions that will form a successful pair with the ith spell. So we are given spells of I and potions of j. So spells of I represents strength of each spell and potions of j represents strength of each potion. And a pair spell and potion is successful if spell cross potion, that is spell into potion, is greater than or equal to success. So we must return an array pairs where pairs of I is the number of potions that will form a successful pair with the ith spell. So let's quickly understand with our examples. So in our first example, we have been given spells array, potions array, and success value, which is 7. So in the given explanation, we can see that in the 0th spell, if we take the first spell of I, that is 5, and we'll multiply with potions array, we'll get values 5, 10, 15, 20, and 25. And out of all these values, there are 4 pairs which are successful, which means the product value is greater than or equal to our success value, which is 7. And coming to the first spell, we'll get values 1, 2, 3, 4, and 5, and we can see that there are 0 pairs which are successful, means there are no elements inside our potions array which is greater than or equal to 7. And coming to the last spell, which is the second spell, we'll take the third value and we'll multiply with each and every element of our potions array, and we'll check how many successful pairs are formed. And out of which we can see that there are only 3 pairs which are successful, which means there are 3 elements whose value is greater than or equal to our success value, which is 7. So we'll return an array with values 4, 0, and 3. Coming to the second example, we'll go with the same process. For our 0th spell, we'll take the element 3 and we'll multiply with each and every element of potions array. So out of these product values, we can see that there are 2 values which are greater than or equal to our success value, which means there are 2 pairs which are successful. Coming to the first spell, we'll take the element 1 and we'll multiply with each and every element of our potions array, and here we can see that there are 0 pairs which are successful, which means there are 0 elements which are greater than or equal to success value. Coming to the second spell, we'll take the last element of our spells array, which is 2, and we'll multiply with each and every element of our potions array. And in this case, we can see that there are 2 values which are greater than or equal to our success value. So for our second spell, we have 2 pairs. So we'll return an array with values 2, 0, and 2. So this is what our problem statement is all about. So let's quickly go through our brute force approach and understand the time and space complexity. The brute force approach is simple and straightforward. So while looking at our examples, we can easily understand the approach to solve this problem statement initially, which is taking each and every spells of I and multiplying with each and every element of potions, and then we'll iterate over our potions array to check how many elements are greater than or equal to our success value. So for each and every spell, we'll get our count and we'll push that count inside our answer array. So for our 0th spell, we'll take value 5 and we'll multiply with each and every element of potions array, which is 1, 2, 3, 4, and 5, which will get answer 5, 10, 15, 20, and 25. And we'll iterate over this potions array and we'll check each and every element and compare it with our success value, and the number of elements which are greater than and equal to our success value will increment our count variable. So we'll also take a count variable which will be initially 0, and this would be reset to 0 for each and every iteration. And after getting our count, we'll push this count variable inside our answer vector. So we'll get 3 count variables and we'll finally return our answer variable, which would contain 3 different values. So this is how our brute force approach works. So the time complexity of this approach would be O of n cross m, where n is the size of our spell array and m is the size of our potions array. And coming to the space complexity of our approach, the space complexity here would be O of 1, as we haven't used any external data structure to store any values. But coming to the answer vector, so this is the output vector, so it is not considered as any extra space. So this is all about our first approach. So let's quickly code this approach and let's submit. So here's the code for our first approach. So here I've taken both the sizes of our spells array and positions array stored in n and m variable. We have also taken on output vector, which is answer vector, where we'll store the successful pair values. We use two for loops to calculate the number of successful pairs. So for each and every spell of I, we'll check with the portions of j, and we'll also use the count variable for each and every spell. So initially the count variable would be 0. After finishing our second for loop, we'll push back this count variable inside our answer vector. So in this way, we'll do this for each and every spell of I, and finally our answer vector would contain all the successful pair count and will return that answer vector. So the time and space complexity here would be O of n cross m, and space complexity here would be constant. So let's quickly run this code. Yeah, it's working, so let's submit. As you can see, this approach gives us time limit exceeded because of the time complexity, which is highly inefficient for large values of n and m. So we need to optimize this approach and to reduce our time complexity so that we'll get a accepted solution. So we'll do that in our optimal approach. So let's quickly move on to our optimal approach. So let's quickly move on to our optimal approach. The brute force approach was O of n cross m, which was too slow for large input. So we need a faster method. So we will be using binary search approach. So the idea behind this approach here would be to first sort the portions array. Since the mathematical equation of our problem statement here is the spells into portions, it should be greater than or equal to success value. So what we'll try to do here is to send this spell to the right hand side, making this particular equations, which is portions should be greater than or equal to the success by spell. So for each spell, we'll calculate this minimum portion strength, where portion value should be greater than or equal to the division value of this success and spell. So to find this particular minimum portion strength, we'll use this binary search across this portions array. We'll get that minimum portions index. So everything to the right of this particular index is a valid portion. So the count here would be that the total number of size of this portion array minus this particular index would give us the total count of our successful pair portions. So this will be our approach. So to calculate the division value, we'll use seal of success by spell. Here both the values of success and spell would be integers, and if we divide these two integers, sometimes we may get decimal values. We will be using seal function, which would generally round up this decimal value to the next nearest integer. If we use the float function, it will generally round down this decimal value to nearest integer. So for example, if the result of our division value would be 2.33, the seal function would round up to the nearest integer, which is 3. Whereas coming to the floor function, if the result value is 2.33, it will round down to the integer value 2. So this might give us the wrong answer. After we'll get this particular value, we'll use this particular value and we'll find the minimum portion strength inside our portions array with the help of our binary search. And to find that minimum portion strength inside our portions array, we first need to sort this portions array. So this would be our first step, to sort our portions array, and our second step here would be to use our binary search. So here we can use two different approaches. We can use our custom binary search method, where we'll use a target, which is the minimum portion strength, and we'll do a general binary search. And our second approach here would be to use the built-in C++ function, which is lower bound, which would give us first valid portion inside our portions array. So after finding this particular index value, and our final step here would be to count the number of valid portions. So if we find our index value here, everything right to this particular index will be considered as the valid portion. So the count here would be that the total size of our portions array minus this particular index would give us the count of successful pairs. So for each and every spells of I, we'll get our count of successful pairs and we'll push this count inside our answer vector, and finally we'll return our answer vector. So this would be our optimal approach, where we are using binary search method to find the minimum strength of our portions inside our portions array, and we are calculating the count with the help of this particular index inside our portion array, pushing it inside our answer vector and returning this. So coming to the time and space complexity of this approach, the time complexity here would be sorting of our portions array would take m log m time complexity, plus finding this particular index with the help of binary search would take n log m. As we are checking for each and every spells of I, so it would take in worst case n, and finding that particular index with the help of binary search would take log m time complexity. So overall time complexity for our second step here would be n log m. So overall time complexity of our approach would be m log m plus n log m. The space complexity of this approach remains constant, which is O of 1. So this is how our optimal approach works. So let's do a quick dry run on this given example 1, and then we'll move on to our code. So our first step in our optimal approach here would be to sort the portions array. So the input portion array is already sorted. So the values here are 1, 2, 3, 4, and 5. Size of our portions array is 5, which is m is equals to 5, and our success variable is 7. So our formula to find the minimum portion strength here is division of success and spells of I. Since we need to round up the decimal value to the nearest integer, we have used ceil function. So based on this particular formula, we'll get the first valid portion inside our portions array. So for our first spell of I, which is 5, the minimum portion strength here would be the ceil of 7 by 5. So 7 by 5 generally gives 1 point few decimal values. So the ceil function of that particular 1 point decimal value would give us 2. For this 2, we'll use a binary search function, find the index where the value of that particular index should be greater than or equal to 2. So that index would be 1. At index 1, we have found a value which is greater than or equal to 2. This particular index is the first valid portion. So to find this count, we'll use this particular formula, which is m minus index value. So m is the size of our portions array, and index value is the first valid minimum portion strength. So the count here would be 5 minus 1, which is 4. So these 4 values will form a successful pair. In the same way, we'll move on to our second spell, which is for value 1. So we'll find our minimum portion strength, which is the ceil of 7 by 1, which is 7. So we'll find an index inside our portion where the value of that index should be greater than or equal to our minimum portion strength. Minimum portion strength inside our binary search function, and we can see that there is no index whose value is greater than or equal to 7. So the index would reach out of this array and would return m value, which is 5, and to find the count value, so which is 5 minus 5, which would give us value 0. Coming to the third spell for value 3, the minimum portion strength is 3, and the binary search would give us the first valid portion index, which is index 2. So it would return index 2, and the count here would be 5 minus 2, which would give us value 3. So we'll take these three values 4, 0, 3, and we'll insert it inside our answer vector as 4, 0, and 3, and we'll return this answer vector. So this is how our optimal approach works. So let's quickly code our approach and let's submit. So here's the code for our optimal approach. So our first step here would be to sort our portions array, also take in the answer output. So use the for loop which iterates over our spells vector. We'll calculate our minimum portion strength first. With the help of this particular formula, we'll get our ceil division. With the help of our lower bound inbuilt function, we'll find that particular index which would give us first valid portion. So it will generally return our iterator. So convert this iterator into an integer, we have to subtract it with our portions dot begin. And for the final step, to count the number of valid successful pairs, we'll subtract it with the size of our portions vector, and we'll push that value inside our answer vector. And finally, after checking for each and every spells value, we'll return our answer vector. So let's quickly run this code. Yeah, it's working. So let's submit. As you can see, this approach gives us successful submissions. So with the help of binary search algorithm, we have reduced our time complexity, which gave us successful submission. So that is how we solve this particular problem statement, successful pairs of spells and potions. So we have started with the brute force approach, which gave us time limit exceeded. And then we have optimized our approach and used binary search algorithm, which drastically reduced our time complexity. and gave us accepted solution. So if you found this explanation helpful, don't forget to like, share, comment, and subscribe to the channel for more daily lead codes and fight solutions. So I'll see you in the next video. Till then, keep coding, keep growing. Thank you.